So I think that pretty well covers the A part of study question 16. The B part of the question deals with the transfer of elevation, and if you again go back to this mining surveying chapter, it talks about using a steel tape. Basically, you treat the steel tape much the same as a leveling staff, only it's very long, and you take readings at the surface and readings underground, and assuming that you then know the distance between the graduation on the tape at the surface and at the bottom, and therefore can add that on to the height of instrument at each level and eventually come up with a height difference. So that's relatively straightforward. The concerns with it would be that you then have to account for the fact that you're using the steel band that's very long and take into account all the different corrections that would have to be applied. And it gets a little more complicated with temperature because of the differences in temperatures. You go down the shaft and there is a formula for calculating the weighted average temperature, which is then used for the calculation of the correction. Also, because the tape is hanging vertically, it's stretched a little bit as a consequence of its own weight, and there's a formula for applying a correction for that as well. That's in addition to the normal tension correction. When we compare the use of a tape horizontally, use of a tape vertically to horizontally, we have with horizontal tape, calibration, temperature, sag, and stretch. The sag isn't there anymore because the tape is vertical. The stretch is a more complicated formula, although there is a separate one to deal with the fact that the tape itself is exerting tension, but there's also the one for the tension different from the tension at the time of calibration. So calibration, temperature, and tension are the same, and then there's an additional one. The temperature is a little more complicated because of the weighted averaging, and there's the one for the tape under its own weight. If we compare using a total station to determine the transfer of elevation, it's similar concern or similar process as we would have done if we had been doing the horizontal transfer. The Taylor-Hobson sphere now has a reflector that has been mounted in a way that it's at the center of the sphere, so we can point to that reflector in any orientation. We point sideways to get to the position. If we then turn it to look downwards, we can measure directly downwards. The only way we can do that effectively is if the total station is capable of measuring in the zenith. Most high precision total stations are capable of doing that, where the carrying handle will swing out of the way and the machine will indeed measure in the zenith, which means you have to turn off the compensation. The other problem with that is that you then have to transfer the center of the total station to some other point, like a benchmark down below, and that requires a process in which you would set the telescope of the total station to be at 90 degrees and try to line up a leveling instrument with it so you could transfer from the center of the instrument over to a leveling staff. And this is a bit of a challenge because of the difficulty in focusing at the crosshairs of the two telescopes. You can do that if you have autocollimation eyepieces that will allow you to look through the eyepiece and also project the image of the crosshairs out to the other instrument. And then there's a bit of contrapulation about getting the things lined up properly, which is usually overcome by having a special instrument where there's an actual little target mounted on the inside of the telescope that would allow the other instrument to focus onto it to get the proper centering. Is there anything else about this particular topic area, underground surveying, that you would like to have discussed?
Oh, hold on, here's a question. Can you describe the elevation transfer with total station again?
Elevation transfer, sure. The best illustration of that would be in this Robinson et al. Paper from 1995, which, as I mentioned, is dealing with the superconducting supercollider. There's several very good diagrams. In fact, I could probably put that up here. It might be easier to follow it if I have a figure being projected here. So we have at the top of the shaft a bracket that holds this Taylor-Hobson sphere that has a target or a prism in it. So it's there'd be two separate spheres, one with a prism like we would normally see in a retroreflector, and the other would have a target. They're both, as I said, manufactured to very high precision so that the target is effectively at the center of the sphere, and similarly with the reflector. So we have with the sphere with a target now at the surface, and we set up a leveling instrument with a way of adjusting the height of the instrument so that when we sight over to the target, the image of the target center will be within the travel of the micrometer of the instrument. And then that would be, I guess, the foresight, and the back sight would be onto the leveling staff that's on top of the benchmark at the surface. So that provides us with a height difference from the benchmark to the center of the sphere. That would be with the target. Now we take that sphere and replace it by a sphere that has a prism, and it would then look downwards. And now at the bottom of the shaft, and in this case it's a tunnel where we could easily set up the total station, we can look vertically with the telescope and measure that vertical distance. Now, like any EDM distance, that would require the corrections for meteorological conditions and also the offset between the mechanical center, which would be where the telescope pivots, and the actual mechanical center of the sphere. But we could do this the same as we would with any EDM prism combination. So that provides us with the distance from the center of the sphere down to the center of the instrument. And then we have to get from the center of the instrument over to a benchmark. And that is done by using the second level placed in a way that when the telescope of the total station is set to 90 for a zenith angle, in other words, the telescope is horizontal, the level would be situated so that the center of the level is within the micrometer travel of the center of the instrument, of the total station's target or crosshairs, as I mentioned earlier. So that would get us from the center of the total station over to the benchmark down below. So you have two backsight minus foresights and the distance between the center of the sphere and the center of the total station, and combining these together would end up providing us with an elevation of the benchmark down below. Now the limitations on this process would be the limitations that there would be on distance measurement, and it's usually electro-optical, so that means there would have to be a reasonably clear line of sight to be able to have the radiation propagate through. There would also have to be a situation, as illustrated here, where the instrument is well supported, and remembering that in many instances this type of determination is a millimeter or better. In this particular case with a super collider, it was almost the same as first order vertical transfer, so that means it's sub-millimeter. That means also then that the total station has to be substantially supported, as does the sphere at the top of the shaft. This is a very simplified diagram. It's quite a process in the actuality to provide all these different supports.